All right, I'm going to show you how to graph rational functions. These are going to be a little bit more complicated than the reciprocal functions that we saw before. However, they kind of follow the same principle. Okay, so what is a rational function? A rational function is going to be defined as any function in the form f of x is equal to a of x over b of x, where both a and b of x are polynomials with no common factors. Before, what that meant for us is that we would have these fractions that look like 7 over x plus 2, where there was a number in the numerator and a polynomial in the denominator. That's not going to be the case anymore. Now we're going to have fractions that look like 2x plus 2 over x squared minus 4, where both the numerator and the denominator have polynomials in them. But in order to graph them, we still want to find the same four things. We want to be able to find both intercepts and both types of asymptotes. So how do we find y-intercepts? We let x equal 0, just like we always have. So that means in this case, we just plug 0 in for the x and end up with 2 over negative 4. In order to find the x-intercepts, what we have to do is let y equal 0. In this case, what that's going to mean is that we'll have to take the entire fraction and set it equal to 0. But think about this. If we have a fraction that's equal to 0, the only way that can happen is if we have a 0 in the numerator and some number in the denominator. If that was flipped around where we had a number in the numerator and 0 in the denominator, this one is undefined. We can't divide by 0. But we can take 0 and divide by a number. That's when we'll get 0. So in general, what I'm going to have to do is only worry about that numerator, the 2x plus 2, and set that equal to 0. In talking about any sort of rational function, that's going to mean we take the numerator, the a of x part, and set that equal to 0 and just solve it. In order to find those vertical asymptotes, remember that that is where the function is undefined. So that's when the denominator has to be 0. So set the denominator equal 0 and solve that. I want to point out that in this case, when we have a polynomial like x squared minus 4 is equal to 0, we can factor that into x plus 2 and x minus 2, which means we'll end up with two asymptotes, two vertical asymptotes. We'll have one at x equals negative 2 and one at x equals positive 2. So that's going to be a new wrinkle that we'll see how we deal with that in a minute. So what about those horizontal asymptotes? Because we're dealing with a polynomial in the numerator and a polynomial in the denominator, we really have a few situations that could pop up. In this class, we're only going to deal with two cases in particular. The first is if the degree of the numerator is equal to the degree of the denominator. So that's a function that might look like this: y equals 3x plus 1 over 4x minus 5. And the thing about an asymptote that we have to remember is that an asymptote is this invisible line in our graph that our graph is going to get closer and closer to way out at infinity. So if we let x go way out to infinity and get bigger and bigger and bigger, what's going to happen is that we'll end up with these numbers that are so very large. Like, think about letting x turn into a billion. If I were to plug a billion into this function for x, we would have 3 billion and 1 over 4 billion minus 5. So that'd be 3999. One more 9 and a 5. If we were to simplify this, just estimating it, even just typing it into your calculator, you would end up with almost 3/4. Because that numerator, that little 1 at the very end and that little 5 at the very end up there, because we're dealing with a number that's so very large, what we're adding and subtracting on the end down here doesn't really affect the overall value of the fraction. What's more important are these two leading terms. So when we want to find a horizontal asymptote, the only thing that I'm going to worry about is the leading terms. So just take 3x over 4x. And simplify that. That means that our horizontal asymptote is going to be the line y equals 3 over 4. So instead of being at the x-axis like it was before, this is going to get shifted up to y equals 3/4, and we do that by looking at leading coefficients, or leading terms. The second situation I want to look at is what if the degree of the numerator is smaller than the degree of the denominator? Something like y equals x over x squared minus 1. Now, because that degree of the numerator is smaller, we could theoretically just rewrite this so that they do have the same degrees. We can look at this as 0 x squared plus x over x squared minus 1. And then again, everything that's over here really has hardly any bearing on the overall value of the function as x gets very, 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 very big. And so we just have to take this part of the fraction and simplify that. So the horizontal asymptote in this case would be 0x squared over 1x squared, which ends up being 0. And in fact, anytime the degree of that numerator is smaller than the degree of the denominator, we're going to have to add this 0 that's up on top. So that means every single time that the degree of the numerator is smaller than the degree of the denominator, the horizontal asymptote is going to be y equals 0. These are the only two situations that we're going to deal with in this class. That is, if those two degrees are the same, we take the leading terms and simplify that fraction. If the degree of the numerator is smaller than the degree of the denominator, then it's always going to be y equals 0. So, how are we going to go about graphing our rational functions? What's going to be our plan? Our first step is going to be to find and plot the y-intercept. Remember that is when we're going to let x equal 0. Next, we're going to find and plot the x-intercept. That's where the numerator is equal to 0. As long as that's quick and easy to find, it's a great way to get another point. After the intercepts are plotted, we'll find and plot the vertical asymptote. That comes from the denominator equaling 0. And then find and plot the horizontal asymptote. That's where we worry about the degrees. If we can come up with a picture of the entire graph from those four things, that's great, and we're done. But sometimes that's not enough. If you have to, take the extra step and get more points. The more points that we have, the more accurate our graph is going to be. So let's try a couple. First, let's have y equals 2x plus 2 over x minus 1. The first thing that we want to find is the y-intercept. Remember, to find the y-intercept, we let x be 0. So 2 times 0 plus 2 over 0 minus 1. That'll be 2 over negative 1, which is negative 2. So we have a y-intercept at negative 2. I'm going to go ahead and plot that point right over here. Next, we're going to find the x-intercepts. To find the x-intercepts, we take the numerator, just the 2x plus 2, and set that equal to 0. When the numerator is equal to 0, the entire fraction equals 0, and that means y will equal 0. So in this case, we solve 2x is equal to negative 2, divide by 2 on both sides, and x equals negative 1. Means we have an x-intercept at x equals negative 1. So I'll plot that one as well. Now we move on to the asymptotes. In order to find the vertical asymptote, we want to find out when the fraction is undefined, and that's when the denominator, x minus 1, would equal 0. So we solve that, and we get x equals positive 1. Remember, the vertical asymptote is a line, so when we draw it, we should be drawing a dashed vertical line. That's going to signify that invisible line that our graph is going to approach. We also need to find the horizontal asymptote. And remember, with that one, we're looking at degrees and taking the leading terms. In this case, The degree of the numerator is 1, because it's just 2x to the first. And the degree of the denominator is 1. It's x to the first. So we just take these two terms, the leading terms, and simplify this fraction, 2x over x. So that means our horizontal asymptote will be y equals 2. I'm going to draw that horizontal line in as well. All right. And now we take a look and see what we got. See if we can graph it. From what I have, because we have these two intercepts, and I have the asymptotes here, I know that my curve has to go through these 2 points. After that, they're going to get closer and closer to both asymptotes. So this is what this one branch of the hyperbola is going to look like. Now I don't know anything else. That's why we're going to need more points. To find more points, all we got to do is pick some x's and plug them in to see what their y value is. Now be thoughtful about what kind of x coordinates you want to pick. In this case, I don't want to pick anything that's going to be less than 1, because I already know what this entire branch looks like. So all of these x values are just going to lie right where I think they are. So instead, I'm going to pick some of these x values to help me out. The best one to pick is going to be the one that's one step to the right of that vertical asymptote. So I'm going to let x equal 2. When I plug that in, that means that y is going to equal 2 times 2 plus 2 over 2 minus 1. So 2 times 2 is 4, plus 2 is 6, 2 minus 1 is 1. That means y is 6. So we're talking about this point where the x-coordinate is 2 and the y-coordinate is 6. And if I go ahead and plot that, that one little bitty point is all I really need to come up with this right branch of the hyperbola. Because I know that my curve has to go through this point, and it's going to get closer to both asymptotes. So this is a very good sketch of what y equals 2x plus 2 over x minus 1 is going to look like. You can always check by typing it into your graphing calculator and seeing what it looks like. So how about when it's y equals 2x over x squared minus 4? Once again, we want to start by finding any y-intercepts by letting x equal 0. So y is going to equal 2 times 0 over 0 squared minus 4. And that's 0. So we have a y-intercept at the origin. Next, find any x-intercepts. The x-intercepts happen when y equals 0, and that will only happen when the numerator, 2x, is equal to 0. And if we solve this, we get x equals 0, which is obvious because we already had a y-intercept at 0. So the x-intercept is going to be there as well. Now, on to the asymptotes. The vertical asymptotes happen when the fraction is undefined, so when x squared minus 4 is equal to 0. So we can factor that into x plus 2, x minus 2. And we get our two vertical asymptotes being the line x equals negative 2 and the line x equals positive 2. So in this case, we're going to have two vertical asymptotes. So two vertical dotted lines, one going through positive 2 and one going through negative 2. So this is already something that we're not used to by having two of these vertical asymptotes. We still have to find the horizontal asymptote. Now, because of the degree of the numerator is 1 and the degree of the denominator is 2, we could think about this as doing 0x squared plus 2x over x squared minus 4, and then only worry about these leading terms, which means our horizontal asymptote is going to be the line y equals 0. So we need a horizontal asymptote, a horizontal dotted line, lying on the x-axis. So we've got all of our important stuff here. Now it's time to graph, and I've got nothing. I've got 1 point, and it's lying on top of an asymptote. Now I don't have to worry about that because asymptotes only talk about what happens way out at x being infinity or negative infinity, or y being positive or negative infinity. So in order to get a better graph, we need to find more points. So maybe first I want to see what's going to happen in this middle region of my graph. So I pick a point that's in there, like x equals 1. If x equals 1, we go ahead and plug it into y, and we'll have 2 times 1 over 1 squared minus 4. That would be 2 over negative 3. So when x is 1, y is negative 2/3, so we're talking about the point 1, negative 2/3. So I'm going to go ahead and plot that at 1, negative 2/3 means it's down, and it's not all the way down to negative 1. That's enough to see what's going to happen from this x-intercept over to the asymptote, because I know that my curve has to go from that 0, that x-intercept, through my point, and then it's going to just get closer and closer to this asymptote. So that's one little piece that I have. I still don't have everything that's in the middle. That means I got to pick another x that's on the other side of that 0. So I'm going to pick x equals negative 1 and see what happens. When we plug that one in, it'll be 2 times negative 1 over negative 1 squared minus 4, meaning that our numerator is going to be negative 2, and our denominator, since it's negative 1 squared becoming positive 1 minus 4, that's still going to stay as a negative 3. That fraction is going to simplify to positive 2/3, so when x is negative 1, y is positive 2/3. Plotting that point, I'll go back 1 and up 2/3. And now I know what the rest of this center piece looks like. It's going to go through my x-intercept and through the point that I just plotted. After that, it's going to get closer and closer to my asymptote. So that's a very good graph of the middle part of this function, but what about everything else? Because I don't have any points there, I need to find them. So let's take a look at this left side and figure out what's going to happen over here first. That means I got to pick one of these x's to plug into my function. And the best one really to pick is always one step to the side of that vertical asymptote. Since my vertical asymptote is at negative 2, I'm going to take one step over, and I'm going to use negative 3 as my x-coordinate. Then I'm going to plug it into the function y equals 2x, so 2 times negative 3, over x squared minus 4. 2 times negative 3 is negative 6. Negative 3 squared is 9, and 9 minus 4 is 5. So when x is negative 3, y is negative 6/5. Which means at negative 3, the y-coordinate is negative 1 and 1/5. So down 1 and a little bit more. That's enough to see what this branch is, because my curve has to go through this point and then get closer to each asymptote. Finally, we got one more section to go through, and that's what's going to happen on the right side. Again, we're going to pick another x value. The x I want to pick is going to be one step from my vertical asymptote. Since my vertical asymptote has 2, I'm going to let x equal positive 3. And plug it in. 2 times 3 over 3 squared minus 4. That's going to be 2 times 3 being a positive 6, and 9 minus 4 being positive 5. So now we have the point 3 positive 6/5. When I plot that, 6/5 is 1 and 1/5, so it goes about right here. And I have enough now to come up with my graph. My curve is going to go through that point and then get closer to each asymptote. And there's a very good graph of now not just that branch, but the entire function for y equals 2x over x squared minus 4. So overall, what we should do first is look for intercepts and plot them. Then go for asymptotes next and draw those lines in as dotted lines. Those are those invisible barriers that we're going to approach way out at the extremes. And only if you need to, find more points. Sometimes you only need 1 point. Sometimes you don't need any extra points, but sometimes you need a handful of them. Take the time and do it right, and you'll end up with a really good looking graph.